Getting up there. You can't see all the grays with the light so low. But welcome back, folks. Looks like we're just about ready to get started. No, we are ready to get started. Looks like we're in week 6. Welcome back, folks. Well, lots of notes to talk about with all the things in black, but so far today, we're just carrying on with what we were introducing last class on the shifting and scaling concepts. For the first time in the entire semester, I realized I could use the actual whiteboard, so this doesn't really make it onto the YouTube videos, but we'll be talking a lot about measures of center, the portions in blue, and measures in spread, the portions in green, or in other words, just the first page here on the notes. But sometimes it's annoying to scroll up and down again on the notes constantly, so we'll refer to stuff on the whiteboard occasionally just to collect information we'll reference a lot. Well, big announcements. Our quiz 4 is due Thursday. We'll have our quiz 5 posted, and I'm thinking for a good quiz 5, I'm going to go for a section 5.4 topic. So the thing that's new about chapter 5 is really section 5.1 was another look at means and standard deviations. 5.2 is kind of an extra topic. It's a side topic in a certain sense. It's important, but the most time we're going to spend on is 5.3. The writing here says it's kind of a warm-up section. And 5.4 is going to be the big capstone section to close out chapter 5. Here we're going to take data, quantitative data, imagine it accumulating into a histogram, and try to model that data just means putting a curve to it, a nice smooth curve that might be symmetric, mound-shaped, and that's the so-called normal models that's mentioned down here. Our calculator is going to be used extensively in section 5.4, so we'll come back to this thought. 5.3 shows us how to get started with really rough approximations, but it's all about the pictures. If you can organize what the picture looks like, even just a mental picture, if that works for you, then it tells you exactly how stuff goes into the calculator. And just a preview of what this is going to look like, we're going to often say hit second and then the vars button. It calls up a huge list of things under distributions. We're going to be interested in the normal CDF. We'll say what that means. And inverse norm are going to be our major operations. And just for a preview of this, let's click this again. If you click on normal CDF, it stands for cumulative distribution function. It's just a way to get area under the normal model or the normal curve. There's a lot of stuff to throw in there. There's a lower bound and upper bound, lower and upper. There's a mu and a sigma. And this is what section 5.3 is really all about. What does the picture look like? If you can draw the picture relative to your problem in 5.4, you'll know what goes into the calculator and what the right order is. So that'll be pretty much what we're going to be spending most of this week on, it looks like. Any questions whatsoever with where we're at or where we're going? Okay, so far this is all just kind of mysterious. If you want to exit out of there, you can just hit enter a bunch of, no, it wants numbers. You could hit second and then the quit button to just get out of there, or sometimes clear is a good way. So we'll revisit all that information and see how that works. But before we even get there, that was just worth bringing it up since it's a big part of chapter 5. We still need to finish off section 5.2. It's not hugely emphasized, but it's still important. So section 5.2 had a theorem, which just means a mathematical fact, which can be proven as true without a shadow of a doubt. And it really has 2 parts. So it's the shifting of the data and the rescaling of the data part. Shifting the data means you took your entire data set. Let's see if we have one here. There it is. Here's an entire data set. Shifting the data would mean I went to every single one of these observations and add 20 to them or subtract 50. The key thing is I'm adding the same number to every observation or subtracting the same number from every observation. And if I do that, shifting the data is going to add a constant or subtract that same constant to all measures of position. So if I add 50 to every value of the data set, I've added 50 to quartile 1, median, and so on, down to the sample mean. Interestingly, it's going to leave measures of spread completely unchanged. You can think of y as a really quick example. If I've added 50 to all these observations here, it means you've also added 50 to the max. You've also added 50 to the minimum, and these would subtract off. It wouldn't change the data values whatsoever. That's one way to think about how that would be affected. So if the min was 700, the max was 800, the new max is 850, and the new min is 750, but it would still be 100 difference between them for the range. Interestingly, the interquartile range won't change, and neither will the standard deviation. Sometimes this is the most confusing one on the list. So that's what this is all about, seeing what happens when we shift the data. Rescaling the data is also important. It's just less confusing. That's why I didn't highlight it in yellow. Rescaling the data means you go to every one of the data values and say, multiply it by 10. Well, you'll multiply all the data values, including measures of position as well as measures of spread, by 10, that same exact constant. So that's kind of nice in a way. Nothing tricky happens with this situation. This is the trickiest part right here, though. Measures of spread are left unchanged if we shift the data. Let's put it in a box just to emphasize. Well, any questions, folks, with that warm up, re-look at this information again? Okay, so one way to see it is, let's take a look at some actual data, not just what's in the calculator. I have a quick data set for a random sample of 15 needles taken from different parts of several Aleppo pine needles located in southern Africa. So let's get a visual of that. It's kind of a weird name. Aleppo pine needles look like these things, I guess, right here on the right. So just your, looks like something that's growing in Idaho that you'd run into potentially, someone's backyard or out in the hills. So we have a whole bunch of pine needles, 15 of them, and they measured, let's see here. What did we measure? Random sample of 15 needles. It's located in Southern California. You know, this is an incomplete context, isn't it? I try to make the context brief since it's more about the theorems. But let's say here, the needles were measured, and I believe this was centimeters, but you know, that should have really been in here in the description. Just noticed that that was missing. Sorry about that. So one of them would be 7.2 centimeters, 10.2 centimeters here on this one, a rather large one. And this is the histogram. Well, I guess that does tell us length in centimeters, but you'd have to read between the lines there on what was actually measured. And that's just the measurements here as a histogram. If you said it's unimodal, skew to the right, that'd be an acceptable answer. If you said potentially bimodal because of this, I'd say it's pretty borderline, but maybe not quite bimodal. Not enough actual accumulation of data in this one spot. The key fact is the sample mean was 9.59 centimeters. The sample standard deviation was 1.59 centimeters. And so now if we do something that is kind of totally random and we shift the data, meaning add or subtract the same constant to all the data values, we're going to shift the mean, but not the standard deviation because this one is a measure of spread. So this measures spread. And this measures, or it's a measurement of location. So here's that same data set right down below. You can see from corresponding values, I'll just highlight a random one. 11.3 minus 5 takes us to 6.3, but we did that to every single data value you see in the data set. Who knows why you'd want to do that, but they've done it. We've subtracted 5 from all of the measurements for the lengths of the pine needles. That means the sample mean should be reduced by 5, and we should be looking at a 4.59. So this was reduced by 5. And this is the part right here. We have to subtract the same constant to all measures of position. And that's what the sample mean was. That's why it's been reduced. but it leaves a measure of spread totally unchanged. So if it was 1.5 standard deviation, 1.59 centimeters in standard deviation, this would be unchanged. And that 5 got out of control. Let me fix that. Does that make sense to folks on this right here? Okay, and if we did something different, say rescale the data, that would mean we took all the data values, say the original ones up here, and multiplied or divided by the same constant. We just can't divide by 0. We'd have 15 undefined statements. But we could divide by 3, we could divide by 100, or multiply by 10. That's what's going on this one over here. Here, all the data values have been multiplied by 10 from the original data set. Suppose we multiply all 15 observation by 10, and this is how the distribution changes. What was at 9.0 is now 90. What we should see happen then is everything from the original data should be multiplied by 10. So this should be 95.9, this should be 15.9, because that's rescaling the data. It says here, rescaling the data would multiply or divide that same constant to all measures of position, all measures of spread. So what was a 1.59 from up here is now a 15.9. The 9.5 is now a 95.9, and that's the new length. And it seems about right. If this is measuring the sample mean that's slightly skewed to the right, we should expect it to be right about there. So it looks right on the histogram as well. At least that's easier to see with a sample mean. So really scaling the data is a little bit more straightforward. Shifting the data can be a little bit tricky because your measures of spread won't change on you, which is very strange. And formulas become really tricky when they do both at once. Some formulas are going to have a rescaling, and at the same time, they'll have a shifting at this as well. So that's the problem that we looked at really briefly last class before we ended. But any questions, folks, on the rundown with these two main ideas? Yeah.
Why would we want to do that in person?
That's a good question. That's something I wouldn't have a good answer for on this, but maybe for something more realistic. Let's say this was the original data here. They went to make a whole bunch of measurements, and then maybe they flew a scientist out on, say, like a volcano or something. Maybe it's a rare tree. And they found out that the tape measure, maybe the person wasn't trained well, or maybe there's something wrong. There's a bias in the tape measure. Maybe when they check that tape measure against something that was a little bit more precise, maybe like the tape or the metal part was extended too far, or they just made a mistake on all those measurements. Instead of flying them back onto that mountain, they can say, well, we know how much all the measurements are biased by on that problem with the measuring device. Add 0.05 to every single measurement to bring it back to its true value. So that would be one possible kind of far-fetched reason why you might want to do that. Does that make sense on that question there? Awesome. Another question here?
I was just gonna recap. So if you're shifting it, that's changing the variables by adding or subtracting them
Yes.
to them.
Yeah.
And that leaves the spread unchanged. So rescaling is multiplying and dividing all of the variables in the data set, and that will change the spread and the y mean or the sample mean.
Yeah, exactly.
Okay.
Yeah, so the one thing that's weird is adding or subtracting the same value to everything leaves measures of spread unchanged. So that's the one that's kind of the odd one out. Other questions at the moment? Okay, so we're going to try this all out again on what looks like the actual real homework problems that you'll see in this section. Kind of a short section, really we're just doing these sort of ideas once again. And this problem is tricky. And you know what makes all this tricky is there's terminology, whole bunches of it, measures of position versus measures of spread. That's one layer of terminology. Second layer of terminology is shifting versus rescaling. That's saying something as well. And the third layer to all this is the actual theorems, these two ideas right here that relate all of it together. So when you really look at this, there's like a whole bunch of different moving parts going on at the same time. So to kind of assist our eyes with this, let's actually take a screenshot of this, throw it into our problem, and we'll walk through what both these statements are saying very carefully as we go to work through this problem. I took a particular approach when I was working with this at first, where I just rewrote the formula. So if you like that idea, you can just rewrite this as C equals 5/9 F minus 160/9. And this could be your new formula right here. Or we could leave it just in this format, right as we see it, and work with it right in that form. I think honestly, it's kind of a toss-up whether which approach is going to be the better approach. Either use the total formula as you see it, or rewrite it in a way that could be more convenient. I like it rewritten this way because it tells me straight out, this part is shifting the data, and this part is rescaling. But you know what, at the same time, if you really look at this, minus 32 inside the parentheses, that's just shifting the data as well. 5/9 times F. Well, sure, it's 5/9 times F minus 32. But that's just the rescaling part. Right there. So that's the shifting and rescaling. So really you have to make a kind of a choice whenever you see these formulas. If you want to do something algebraically to it, might not be a bad idea. It's a little bit easier to work with. Or if you decide to leave it in this form, that could work just as well. We briefly saw how it goes at the end of last class on Thursday if we did expand it. How about we leave it in its form and just work with it as we see it? Does that sound all right to folks? Okay, let's try it out that way then. And if you'd like to see it from a different approach, I'm happy to show how that should go as well. Well, we should read the problem. It says, a study of 130 healthy men and women found that the mean temperature was 98.25 degrees. So right away, we want to think, is that a measurement of position or is that a measurement of spread? Any volunteers for which one this should be? Absolutely. The mean is going to measure position. Really, the better way to think about it is spread is the one with very few statistics, and the ones that are most likely to come up are interquartile range and standard deviation. So if you think of those as the ones for spread, everything else is position. So we have a value for the mean. Y bar is 98.25 degrees Fahrenheit. We're told the standard deviation was 0.73 degrees Fahrenheit, but that's measuring spread now. So S for standard deviation, 0.73 degrees Fahrenheit. And that was supposed to be F for Fahrenheit there. We're also given a min temperature and a max temperature, but those are also measurements of position. So let's write them in as min 96.3 degrees. Max is 100.8 degrees Fahrenheit on both. Then it tells us find the mean, standard deviation, min and max of the temperatures in Celsius. Well, if we're going to go to Celsius, this is the fundamental formula. I guess this is the better answer to why we'd want to shift or rescale the data. You might be publishing in a journal that just wants Celsius as opposed to Fahrenheit. If all your values are in Fahrenheit, then we have to make these computations happen. So everything that is a measure of spread, doesn't matter if we've rescaled or we've shifted the data, we have to do the same with shifting to all measures of spread, or excuse me, to all measures of position. Hang on, let me look at my color coding. I think I got this flipped. That's not going to help out. Sorry about that. Measures of position should be in blue, or else this is going to be really hard to look at. Seem to be doing that a lot lately. Sorry about this weird issue here. Green for the measurements. A spread, okay, that's gonna be a little bit easier on the brain, and darn it, let me change these out really quick as well. If you're not writing in colors, you don't have the same problem, but so mean Y bar was 98.25. Then min 96.3 degrees. Max is 100.8 degrees. There we go. And standard deviation S, 0.73 degrees Fahrenheit. Okay, that'll be a little bit easier to work with. Sorry about that distraction there. So this is the rescaling part when we do the 5/9 multiplying. This is the shifting part. But if we shift the data, then measurements of position are going to be shifted by the same amount. Shifting is going to be minus 32, so it just tells us we'd be subtracting 32 from these. And when we rescale the data, that's 5/9 multiplying, we'll multiply by the same thing in all measurements of position. In other words, it just tells us we use the whole entire formula. So that's a better way to think about it. So for example, the new Y bar is going to be 5/9. The old temperature reading in Fahrenheit, but that was the 98.25. Then minus 32. And that's all we have to do to work through this problem. We just have to be worried about anything that was a measure of spread, because that's the one time the formula does alter for us. So at the moment, it's really just a big calculator problem. Go 5/9. If you're typing this left to right as you see it on paper, you can just go parenthesis right here, and the calculator would use the order of operations correctly, the way we've stated it right here. 98.25 minus 32. And that's our new measurement in Celsius. It didn't say what to round to, so let's go for 1 decimal place to match the input. Well, some of them are to 2 decimal places. I'll keep the same amount of decimal places as we see in the data. So this would be 36.81 degrees Fahrenheit. Excuse me, degrees Celsius. And we made the temperature conversion. So far, it feels like these ideas are just kind of not a big deal because we're just using the total formula. And that'll be the same for the min and the max. That's just because they're measures of position and the whole formula is affected for those. So another run, min is 5/9. The minimum was 96.3 minus 32. So up on the calculator, we'll go 5 divided by 9, 96.3 minus 32, just like that, and we get 35.7 degrees Celsius. Then just redo it again for the maximum. Max is 5/9. In place of F, we put in the Fahrenheit value we had, which was 100.8 degrees. Then subtract 32, that's the rest of the formula, and we'll have a value. So 5 divided by 9, 100.8 minus 32. That gets us to 38.2 degrees Celsius. And one last one to go, the sample standard deviation S. Well, any questions so far, folks, to this stage?
I asked you this last time.
Yeah.
Where did you get the 160 from? It was red, in orange,
In the
160
Oh.
over 9.
Oh yeah, gotcha. So that was taking the 5/9 times the negative 32. So if you rewrite this as Celsius, take the 5/9 here, minus 32 times 5/9. This whole thing here gives you the negative 169ths.
Gotcha. It's just that formula rewritten in a different way.
Yeah, exactly. And we could have put this whole thing in the calculator in that formula as well. We could have gone 5/9. Take the value for the Fahrenheit, which is 100.8. Oh, whoa. Let me bring that back. There we go. 5/9 times 100.8, then minus 169ths. And we get to 38.2 once again. So same formula, just in a weirder format. Other questions so far? Yeah, absolutely. So let's try it again. Last one is rewrite the new measurement of spread, the standard deviation. And here's where it's suddenly different out of nowhere. This is a tricky section because when you're doing it on the homework, it feels like everything is just the way you would expect because almost everything is a measurement of position, right? But once the measure of spread comes in, suddenly it feels like algebra broke. Things are working differently. And it's because of this part. When you shift the data by, say, subtracting the same value from all observations, the measurement of spread will be unchanged. So for the standard deviation S, it's as if this part doesn't matter, and this is your whole formula. Formula is Celsius 5/9 times F. And we totally just abandoned the negative 32 because that's the shifting part and it doesn't change the spread of the data whatsoever. Again, this is weird because this is something you would almost never do unless this came up specifically as the context. S was a standard deviation and you're shifting the data in this specific way. So that means for S, we would take back into the calculator, 5 divided by 9, multiply by the old standard deviation, 0.73. And that's it. That's the whole formula. Really kind of weird in a way. We get to 2 decimal places, 0.41 degrees Celsius. Again, it feels kind of weird in a certain sense. But the thing I like about this problem is there's kind of a built-in check into it as well. Suppose we did use the whole formula. This is what it would have looked like. We're going to plug in place of F, the 0.73 degrees Fahrenheit, go 5 divided by 9, multiplied by 0.73. Then you'd have to go minus 32. And here's where it gets weird. Remember, S measures how spread out things are. At the minimum value, the sample standard deviation is 0. And that would mean all of your observations are identical. All 130 healthy men and women had the same exact body temperature. That'd be really weird, first of all, right? Everyone to the decimal point is exactly the same. That is almost impossible in data. Real data has variation. People are different from one another. So your standard deviation S is 0 at minimum. If you use the whole formula, you get something worse, something negative. So this would be your tell that something is really wrong about this. The data wasn't wrong. It was just that shifting the data means subtracting 32 is not even relevant to this formula. You wouldn't get the right standard deviation at all. And just to recap those thoughts, S, which is equal to the standard deviation, is 0 at minimum. Related topic, different way to say it. S is never negative. Just like the range can never be negative, just like the interquartile range can never be negative. Any measurement of spread is 0 to say everyone's identical, but more realistically, some positive number. The larger the positive number, the more spread out your data is. So a really weird kind of problem, right? Any questions at all, thinking about it in these different kind of ways? Okay, well, this stuff can come up if you're taking, say, a chemistry lab, a biology lab, doing something in, say, ecology potentially. Anytime a standard deviation comes up or an interquartile range comes up, and you're maneuvering through different formulas, this could be a problem that shows up just out of nowhere, and it's easy to miss. And that's kind of the reason we're doing this kind of a side topic in section 5.2. It's all about handling data, and this is one of the weirdest things, really, in my opinion, so far in the book. We'll try it one more time just to get another feel for how these kind of ideas go. But any last questions or comments getting through this one? Okay, here's another problem pretty similar to what it could look like as a homework question. This one feels kind of similar to some data we've looked into. I think in the last section, 5.1, we're dealing with what looked like SAT scores and ACT scores. And this one time, in example 3, it just says exactly that's what it is. Each year, thousands of high school students take either the SAT or the ACT standardized test, they tell us. I only took the ACT test, took it once. I don't remember getting very great scores on that. Some people take it multiple times. And the reason they probably do is they're trying to get into a specific college and they look at that data. They tell us next, combined SAT math and verbal scores go as high as 1600, while the maximum ACT composite score is 36. And since the two exams are use very different scales, that could be a problem for some colleges. Maybe one college uses SATs as a standard, and all you took was the ACT test. So that's one context where a formula is now handy. We want to make a comparison, and a convenient rule of thumb is that the ACT score is 40 times your ACT score, add 150. So that's probably not a perfect way to convert between the two, but that's their rule of thumb. It goes on to say, an admissions officer reported the following statistics about the ACT scores of 2,355 students who applied to, that's a typo I've never noticed before, their college one year. Spelling is hard today. There we go. So here are the data they gave us: the minimum, the mean, standard deviation, third quartile, median, and interquartile range. Really, our job is to decide which one of those are measurements of spread, because those are going to be the ones that do not use the full formula. A formula has two parts. This part is the rescaling. Rescaling is going to affect every single statistic. But this part, the plus 150, we're shifting every data value to the right. From the ACT, add 150, is a shifting. Because that's a shifting part, we have to be really mindful of this part right here. Measures of spread are going to be unchanged. In other words, we won't even use that part of the formula. So that means we have to find those measurements of spread. Standard deviation showed up, just like in the last problem. But there's one more. Anyone spot which one it is? Yeah. Yeah, good eye. So the IQR is the only other one that's different in this whole list. Everything else, that's just a measurement of position. So that's lowest score, or said another way, minimum. The mean, or said slightly differently, that's just the Y bar. Quartile 3, that matches our language, and median, we just usually shorten that up and say M for median. So we want to take all these data, these are now as ACT scores of the 2,355 students, find their SAT equivalent using the formula above, that rule of thumb. Really, let's start with the weird ones this time. For the measurements of spread, we use the following. By the theorem above, when it says leaves measures of spread unchanged when we shift the data, literally just means lose that part of the formula. The plus 150 is irrelevant. Kind of like how we didn't use the minus 32 part of the last formula. So for spread, SAT is 40 times ACT. So this is a pretty decent strategy, I would say. Should have done it on the last problem. If you look for the thing that's weird first and just handle that, the rest of the formula work is going to be the way you would expect it to work. So let's rewrite each one of these. Standard deviation S is going to be, this is an ACT value of 3, so it goes into that part of the formula. It'll just be 40 times 3. So 120 points as an SAT is the spread of data for the 2,355 students. Do it again for IQR, kind of more friendly values here. This is going to be 40 times, the IQR is the ACT part we substitute here, so times 3, excuse me, times 6, which is going to be 240 points. So this value of 6 just dropped in there. We multiply it by 40, and now we have our new measurements of spread, but now as a SAT scale instead. We just have 4 more statistics to go, but any questions at the moment? Okay, so now, whatever the formula is, we just use the whole entire formula when it comes down to the measurements of position. So for position, use the full formula, that SAT equals 40 times ACT plus 150. Pretty much we're through the tricky part of the problem. It's just a lot of calculator computations. So the new min, seeing the formula over here, all we're going to do is replace this part right here, highlighted in yellow, with the values we see on the original data, or the original statistics. So it'll be 40 times 19 plus 150. I've lost the ability to do these in my head, so let's hit this with the calculator now. 40 times 19 plus 150. So that gives you a minimum SAT score of 910. And then it's just rinse and repeat. Same process, new statistic. Does that make sense to everyone, how we're getting the new data? Okay, trying it out again. Y bar, take 40 times that value, which was 27, then add 150. So the mean SAT score by the rule of thumb is going to be whatever that comes out as. 40 times 27 plus 150. And we're up to 1230 as an SAT score mean. And just 2 more to go. So next is quartile 3. 30 times 27 plus 150. By the way, we haven't used too many calculator shortcuts, but if you want to speed it up, here's what it would look like. First, let me make sure I've got the right value. Quartile 3 is a 30, so let me fix that there. Looks like I put my values in weird spots, actually. I think I just messed up that whole formula. Let me just start over from the top. It was supposed to be 40 times the old quartile 3 value, which is 30. So should have looked like that. So that's a better value. And now what I was going to say is, in the calculator, we're just changing this value right here. The 27 is just going up to a 30. So a good speed up is click the up arrow on your calculator, enter, left to this position, and just overwrite the 30. And that could save you some decent time. So 1350 as a SAT score. Last one to go is the median M. So 40 times new value, which is 28. Excuse me, the old value is the ACT score, which is 28, plus 150. And if you're gonna use a shortcut again, just hit up arrow, enter, left arrow to this position and overwrite the 28. So now it's a 1270. So that was 6 statistics transferred over through this formula. The only thing we really had to be very careful and mindful of was anything that was a measurement of spread. So see the color coding above on how we kind of tied those together. Any last questions at all, folks, finalizing that last problem there? Okay, well, again, the big takeaway with this is anytime you're dealing with a statistic and it's going to be worked through a formula like this, it can be really tricky. I mean, some cases it might not be that bad because if you change the data, like from here to here, you could have just put the data into your calculator and crank these out. So if you wanted to, you can put 15 values in, see if those statistics are right. Put these 15 values again in the calculator, see if these values are right. And that's a quick way to just know you have the right values. But if you don't know what your values are, we're just told we have 2,355 students. If this is all we've got, then these ideas become really, really important because this is the one-off. Any measurement of spread, the formula has to be used in a very, very careful way by ignoring anything that's shifting the data, by adding the same constant or subtracting the same constant. But for everything else, the formula works as normal. So that's our wrap up on this topic here. What we'll go into next is what we started out discussing in class, talking about the normal distributions, the normal models. But any last questions or comments before we close this out? Okay, let me make sure that the save takes on that. And now we're going off to the next section, 5.3 on the normal models. So the way it starts is kind of vague and strange. They throw a graph at us. We have a whole bunch of percentages. We have an empirical rule, which is also called the 68, 95, 99.7 rule. But a good way to view what we're about to do is going all the way back to chapter 2 and looking into some quantitative data. So that would be section 2.2. Here's what we were doing in the past, and we looked at this briefly, I think, earlier. We're taking quantitative data like this, seeing how to display it. One way was the dot plot, a quick and dirty way to just see where your data is and what the rough shape would be, symmetry versus skew. But this is another way we started looking into data. Histograms play a special role. We're really interested in the shapes of those histograms. If the shape is just right, we can use certain ideas, such as the normal models, to model that said data. This is all kind of vague still by just saying that. Let's look into another one in section 2.3. We like our data to be at least roughly symmetric. And this was that kind of data. It's definitely at least, well, it looks highly symmetric. For these data, think of the histogram that we see here as kind of just a rough snapshot in time. What we want to do is smooth this out and imagine, what did the population really look like? This is just randomly selected individuals from the population, but the population itself may have looked more like this. We'll draw a smooth curve that goes through the heights of the rectangles in the histogram, roughly. Let me try to do it a little bit better. A curve that looks about like that. So we're trying to fit a curve to a data in this kind of way. And this is what we mean by modeling. Taking a curve like this to describe all the data that we have in the sample. The reason we might want to do this is it's not necessarily the sample data that we're trying to study. What we're really trying to study is the underlying population itself. That kind of goes back to inferential statistics, like we were talking about at the start of the semester. If we have sample data, and we want to discuss or model the population, this smoothed out curve is now our way of saying this is what the population actually looks like. And the histogram underneath it, that's just a rough snapshot with the limited population size. So finally, that's what this curve is trying to do. If our data looks at least roughly symmetric, these curves are going to tell us a way to model the underlying population from which the data came from. And there's lots of weird facts about this curve. Let me close this out. My computer's working kind of hard as it is. But the first thing that we want to talk about these data is the interesting role that the mean plays relative to the standard deviation. We kind of hinted at this a little bit when we first defined the standard deviation. That was way back, I think, in section 2.5. When we first worked with the standard deviation, SD is how it's written here. Let's maybe write in our own notation as soon as the computer catches up. There it goes. We usually write S for standard deviation. For mean, we often write Y bar. We'll look at different ways to describe these things, but for the moment, this is the tie-in from the section 2.5. And we cited this. It's hard to say what the standard deviation S is really doing, but a rule of thumb is to say, if your data is at least roughly symmetric, mound-shaped, or unimodal, then about 68% of the data is going to be within one standard deviation of the mean. And by one standard deviation of the mean, we mean from here to here. The mean is in the center, go left by one standard deviation, go right by one standard deviation, and that would be 68% of all the data. Well, if we break this up into regions, that'd be 34% on the left, 34% on the right. So that's what this is trying to tell us all together with the 68, 95, 99.7 rule. The 95 part of the 68, 95, 99.7 rule just says, well, if you go 2 standard deviations to the left or the right of the mean, that's just about everybody, 95%. So that would be from here to here where that heavy yellow bar is. Doesn't really shade too well everywhere. So let me just go on the horizontal axis. And sure enough, if you check this out in the calculator, add up all 4 of these percentages that you see here, 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 and here, that should be 95%. Seeing is believing, so let's double check that. Well, the middle two sum to 68 all together at 13.5. There's 2 of them, so you can just go times 2. And that takes you to the 95% from the empirical rule here. Does that make sense to folks on what this rule is trying to say? Okay, well, there's 3 parts to the rule. The third part of the rule says 99.7, about 99.7% of the observations, so nearly every piece of your data, should be within 3 standard deviations of the mean. So that's going from way out here to all the way out here. And if you took and added up all of these percentages that you see circled, it would total to 99.7. So that's the last part of the empirical rule. I'll often say the 68, 95, 99.7 rule. I think that's the better name, even though it takes more words to say, because it's also helping us remember how the rule works at the same time. But abbreviated, it's just the empirical rule. Empirical means it comes from taking summary or sample data, empirical data that you actually have, and trying to model it. So this is what it all looks like. But when you really stare at this, these are percentages. They add up to 99.7, so some parts of the percentages are missing. Notice that it keeps on going towards the left right out here. This curve, even though it's not easy to see on the graphics, has several interesting properties. This so-called normal model or normal curve that we see plotted is this line right here, the solid line. So this is the normal model. Often simply said or called the normal curve. interesting facts about the normal curve is it goes to the left and to the right forever, so it has an infinite extent. Just trying to figure out where is a good place to say this. The curve, let's maybe put it over here onto the right. The curve does not stop. It goes to the left and right forever. So it's an unending curve. You could put arrowheads on that, but I don't want the sketch to get too busy. But if you put a little arrowhead on it like that, that'd be one way to convey it. But this is already informationally dense as well as it is already, so I'll leave that part off. Other interesting fact about this is the curve never touches the horizontal axis. And that's kind of well conveyed here. If we zoom in on it on the left or the right, this curve was meant to show about what it would look like. When you're beyond 3 standard deviations, it is extremely close to the horizontal axis, but it will never actually intersect it. There's always a positive distance between this axis and the normal curve. That makes the next fact even weirder still when you think about this. This is a true mathematical fact, so if this is kind of strange to you, I can send you some videos or some other ideas to help out with this. The area under the curve is finite. The next section will say exactly what it is. That's when we'll start to use the calculator computing these percentages that we see here, or you could call them probabilities, and you're really talking about the same exact idea. So it's a pretty wild curve. Goes to the right forever, to the left forever. The area is finite. That's why it makes sense to talk about percentages. It also means there's something missing here. It would be nice to complete this chart, and I'm not sure why books don't do this. It'd be nice to know what percentage goes to the left of 3 standard deviations, what percentage goes to the right of 3 standard deviations. In fact, this will be really helpful for the homework exercises as well when you go to do these in MyLab statistics. So that's going to be our next thing to calculate. What are those 2 percentages to totally complete the diagram? First, any questions at all with these 3 random facts about the normal model or the normal curve? Okay, so if we want to find out what's in the far right extent or the far left extent, really we just want to use this part. 97% of all the observations are within 3 standard deviations. So that's going, following the yellow, all the way to this borderline, right where the 2.35% ends. Going to the left, that'd be all the way to this borderline, right where this 2.35% ends on the left. So if that's 99.7%, and we have 100% of area to account for, we can just take 100% minus 99.7. And this is the amount that's in both the far left tail out here and the far right tail out here. So all we have to do is divide it by 2. This curve is totally 100% perfectly symmetric. So the moment you go division by 2, that's the exact percentage in the far left tail and the exact percentage in the far right tail. So we can fill in the question marks and go 0.15% on the left, 0.15% on the right. So that's the situation so far. The key thing about this curve is we're taking actual real sample data and seeing, will one of these curves fit on the data? We might have to move it left or right. Might have to shift where the center is so it lines up with this samples mean. We might have to compress it or stretch it out so that it lines up with the sample's standard deviation. If we do that, now we're modeling the population's data using the sample data itself. So this is our first look at honest inferential statistics. But it doesn't always work. You can imagine when we were way back in section 2.2 or 2.3, some of our data just looked really awful. Let's take a look at some of it. This was wonderful data, but if we go to the very bottom here, these data were no good. You can imagine what goes wrong. If you try to draw a normal model to this, your model might look okay going off to the right. But when you go off to the left, there's no data out here to match where the area is under the model itself. So when our data is skewed, noticeably skewed, we can't model it by the normal distribution any longer. The good news are other distributions that could fit it, but just not this one. So we're on the lookout for these kinds of data that are skewed enough so we would never call it roughly symmetric in the first place. And that's what the nearly normal condition is all about. That's kind of a fun name. If the shape of the data's distribution is unimodal, at least roughly symmetric. So that's where nearly normal comes into play. And there are no obvious outliers. So outliers are going to throw all of this off. This condition is required in order to model the data using the normal model. So in short, we can fit this normal curve there on top of our data as long as it's not too skewed, as long as there's not influential outliers messing up the symmetric shape you'd see. We'll try that out on a couple problems just to get a feel for when can we use a normal model. That's just as important as knowing how to use it in the first place. And here's a couple scenarios using this nearly normal condition. So this is some interesting context. If you're into the veterinarian sciences, probably doesn't seem that morbid, but for a lot of people, it's kind of wild data. This is real data as well, it turns out. We're told a veterinary anatomist investigated the spatial arrangement of nerve cells in the intestine of a pony. So this is possibly some concerned owner of this animal that went to a specialized veterinarian for some kind of problem. What the veterinary anatomist did was remove a block of tissue from the intestinal wall, so just a small sample really, but then took that block and cut it into many equal sections. So we have a whole bunch of equal sections, 23 of them altogether. So the sample size here is 23. And counted the number of nerve cells in each of the 23 randomly selected sections. I'm not too sure why they would be so interested in nerve cells, but possibly something to do with this animal's condition. And this is the data they got. So this was just for one section of the intestinal wall. You might imagine that all around that section, the data probably looks about the same, and maybe we can model this data. These data, if you look into it, it looks like it is unimodal. There's one main peak. If you say it has a skew, what direction would you say it favors, left or to the right? Yeah, if this is the main peak right here, then these values right here are causing a bit of a left skew. So it has a left skew to it, but you know, we're pretty forgiving when it comes out, when it turns to skew. This is not skewed to the point of being in violation of the nearly normal condition. We would say it's still roughly symmetric. Left skewed, but roughly symmetric. There's no outliers in these data, so that's helpful. No outliers. The question is it reasonable to model these data using the normal distribution? And we would say yes, it meets the nearly normal condition because this part right here wasn't violated badly enough. So we can say yes, we can use, it says normal distribution, or you could say normal model. that's worthy to put in the notes right here. Normal distribution is considered synonymous with normal curve or normal model. So same as normal model. And another way to think of this is you can imagine just trying to fit one of those curves that we're studying right up above, something like this, to the actual data. If you gave it your best shot, it might look something about like this. It doesn't look too bad. So this kind of curve would be okay to try to model it with a normal distribution. Definitely not perfect. It does show that there's some asymmetry. If I try to make my curve perfectly symmetrical, it probably would look a little bit more like this. But that's not too badly off. So we could start to model the underlying population with a curve like this. We would just need to know what is the mean of these 23 observations, probably somewhere around maybe 25 or even a little bit less nerve cells per section. We'd want to know the standard deviation. Once we have those two key values, we can put percents on what we expect here and number of nerve cell counts along the horizontal axis going this way. So this one is not a bad case. It'd be nice if the data was more symmetric, but real world data is almost never perfectly symmetric. And so that's why this is a statement that you see coming up a lot. In fact, if you go through these notes again and see some of the tables and charts we put down, we've often highlighted this data is at least roughly symmetric, just to train our eyes on what that would look like. So now here's a case where the data looks really bad. And these are data we've seen before. This is the so-called 2015 Urban Mobility Scorecard. It measured the loss per year in millions of dollars due to traffic congestion in the 13 largest urban areas in the United States of America, with a population of over 3 million. These data were highly skewed to the right. So if they're asking us if it's reasonable to model these data with a normal distribution, on one hand, what would it look like? We try to line up the peak with where the mode is, where all the data is accumulating. It is unimodal as well. And so if we try to put a curve to that, one end of the curve could look like this, and that's not too bad yet, except the other end of the curve has to go like this, and there's no data out there whatsoever. Here, there is data under the curve no matter where we drew it, but once it looks like this, once it's skewed far enough to the right, this normal model is going to do a terrible job trying to model the population. We just need a different kind of curve to make it work for us. So when it asks, is it reasonable to model these data? We might just say no, because, well, two problems. The nearly normal condition wanted roughly symmetric, and we didn't want outliers in our data set as well. So we see both. We'll say no because these data are strongly skewed to the right with outliers. So with this data excluded, it would just need a different kind of curve to make it work. And the more statistics and probability you take, the more you'll discover those curves. If you're curious on what it would be, it'd be the so-called exponential model or exponential distribution or exponential curve. Much like this one's called the normal model or normal curve or the normal distribution, the exponential model handles skewed data. Really, this comment is in orange just for the sake of, it's good to know that there are ways to handle even the worst data we could ever possibly see. We can always fit a curve to it some way, somehow. Well, this is the introduction to what the normal model is, how to work with it. Next thing we're going to start to take a look into is how to actually make predictions about the population based upon summary data that we have and using the normal model. Any last questions about the nearly normal condition, when we can use the normal model or not? Okay, here's what the next set of problems are going to look like then. The empirical rule makes a comeback, as well as this handy little table right here, or graphic. We discovered that on the ends, it's 0.15%. So just as a reminder, let's put that in. And we did use a Y bar in this position and an S in this position, but we're about to make a slight change. Really, this is just a new point of view. When we put this curve on top of sample data, we're no longer really concerned about the sample any longer. Really, what we're going to try to do is this thing all the way back from chapter 1. Let's take another look at this graphic. In chapter 1, what we really want to do is work with a parameter, but we knew that the parameter was unknown, so we went to a sample. These are categorical data, so the statistic is a p-hat instead of a y-bar. We'll be calculating those statistics a little bit more as we go through the chapters. But once we got the sample, we said the parameter that we really want to discuss is well approximated by the statistic. This same idea comes back because once we put a normal model on top of our data, we're describing the population now, and that means we're using parameters which describe that population versus statistics which describe the sample. Finally, it's been a while, this comes back to us. We have a normal model here that's going to sit on top of a histogram, and we'll refer to it as n mu sigma. But mu is just referring to the population mean. And I'm noticing I have my colors backwards. So we're going to refer to that as mu. Sigma, this is a new symbol for us as well, refers to the population standard deviation. And that's going to be the sigma value there. These are weird statistics, but the idea is mu is going to describe the population, so we need a whole new symbol because y bar describes this mean of the sample or the sample's mean. Typically, mu is unknown, but if we're going to model the data, we put in a value, and this is literally what we're going to do. We're going to say the mean mu is approximately equal to y bar, which was the sample's mean. And the other new symbol, sigma, this is a weird one. And by the way, when you draw your sigma, basically you write the letter O with just an extra tail coming off to the right. So that's your sigma. If you recall, that summation symbol is uppercase sigma. So you learned a lot of Greek and statistics. This is now just lowercase sigma. Lowercase sigma is the statistic, which is going to describe our whole population, but it's approximately equal to the sample standard deviation S. Sample standard deviation. So it's weird to throw in these new symbols, mu, and by the way, when you're drawing mu, it feels like you're doing the letter U, except it has a forward tail coming down like that. Just kind of an interesting one to draw. Usually you start by drawing the tail first, and then just imagine you're doing the letter U as you come back up. So this is going to be how we describe the mean of the population. And this is how we're going to describe the standard deviation of the population. In fact, we'll use those same symbols a lot in chapters 12, 13, and so on, when we're doing inferential statistics even more. Now, finally, what is this saying? This says we're modeling our data with n using the normal distribution. So that's just a shorthand for the normal distribution itself, or the normal curve. And we're also saying that the mean is going to be right at mu, whatever value that is, and the standard deviation is going to be whatever sigma is. Well, we'll come back to these ideas when we go to look into what's going on in example 2. But the idea is, example 2 gave us a mean value, 1.31, gave us a standard deviation value, 0.42. That's going to be our mu and sigma when we go and take a look into this next problem. Well, sorry for going right down to the last minute on this one. Any last questions or comments on dealing with any of this new terminology? Okay, well, have a great evening, folks. We'll be right back here, seeing how the problems actually work when we come back on Wednesday's class. Then we'll practice it some more in the calculator after that. Oh, I see what you're saying. Yeah,
So I did it through Canvas, I'm hoping it worked.
usually anything sent through Canvas sends me an extra email. And yeah, I see it came through at 8:17 PM. And I have a download link, so that should work out just fine. Let me double check. It's downloading.
Sorry.
Yes, it is a JPEG file. So yeah, it looks like it came through just fine. Yep, no problem.
How much shifting and scaling can we expect to see to come?
Not too much.
Oh,
Really kind of a side topic. I don't know if it's gonna be a big part of exam two, but it's something that might come in as like a side question on the final exam.
Okay.
Couple problems to practice on the homework, but it'll be kind of a small part of the course.
Thank you again, Jan.
You too, have a good one.
Oh.